Thank you. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for the students. Just ask you to bless this class as we prepare for test 1, Lord. In your name I pray. Amen. When's your test? Tuesday. Yes, very good. Megan, you were about to ask me a question about something.
To what extent do you need now the information about the centripetal force? Is it just the more equations that we derive, or more the extensive questions you had in your text?
Well, let's see here. I think that, like, I ruled out part B of the question we talked about last time, number 27, right? So if you can tell me the specific problem you're thinking of, then I can tell you whether or not it's ruled out.
I can't think of a specific problem. I just didn't know if we needed to be able to derive the equations that we got for the centripetal force, or just
Deriving, so the centripetal force is just this, ma equals to v squared over r, where the acceleration is center seeking. So this is in the case, well, okay. This is true even for non-constant speed circular motion, but when I actually ask you to work out a question that involves circular motion and the force law, you pretty much can use mv squared over r is equal to the net force, and that net force must be center seeking. So that's that idea and its applications. We looked at the geosynchronous orbit problem, and also we derived Kepler's third law. So those would be 2 good problems that I might ask you. Or I might ask you something more, computational that's specific, like find the radius of the orbit of Venus, given that its year is X number of Earth years, or something like that, right? That's a reasonable question. Does anyone, I can look it up, but it'll take me a minute. Does anybody happen to have their recommended homework list just sitting in front of them so I can scan through it right quick?
I do.
Okay. All right, so I have recommended, so we're talking about chapter 5 at the moment, yeah? Which is page 132 to, what is that? Oh, I'm sorry. Yeah, 132 to 136 in terms of questions. Now, I've recommended you do 5, 7, 9, 11, 13, 19, 25, 27, 29, 31, 33, 35, 37, 43, 45, 49, 73, and 75, and 89. Those are problems on page 132 to 136. I will now take a minute or two to look at these problems and tell you whether or not I still think those are legit, given what we've done, okay? Number 5 on page 132. A ball attached to the end of a horizontal cord revolves in a circle of radius 1.3 meters on a frictionless horizontal surface. The cord will break when the tension exceeds 75 newtons. What's the maximum speed the ball can have? You would love to have this on the test. This would be a wonderful test question. How do you solve this? You have a ball, and it's going in a circle on a table, right? What makes it go in a circle? The tension force, right? And so that tension force is equal to ma, well, mv squared over r, because it's going in a circle, right? So what do they give you in this problem? They told us the radius. They told us the mass. They told us that the tension can't be more than 75. You just put those numbers in, and you do what? Solve for V, right? So number 5 is a reasonable question, okay? You can solve it with t equals mv squared over r. That's not a bad problem. Number 7, a car drives straight down towards the bottom of a valley and up the other side of the road, whose bottom has a radius of, at the very bottom, what's the normal force? At the very bottom, the normal force on the driver is twice his weight. At what speed was the car traveling? So I'm going to rule out that question because we just haven't done enough with that at the moment. So you can skip number 7 if you want to. Number 9. what's the maximum speed which a 1,200 kilogram car can round a turn of radius 90 on flat road if the coefficient of friction between the tires and the road is 0.65? Is this result independent of the mass of the car? This is probably not fair until I do the following. So let's work it out. So, going around this turn, right? Number 9, yeah. Going around a turn, it's got the car mass 1,200 kilograms. Great. And the radius of curvature here is 90 meters. The radius of the turn. Flat road, coefficient mu is 0.65. So what's the maximum speed which the 1,200 kilogram car can turn around the radius, make this turn if that's the coefficient of friction? All right, flat road, very good. So what keeps the car going in a circle? Like what's going on? I mean, what's the complete? It's a three-dimensional problem, right? So you could also think about the off the board kind of direction. And so if I can draw that just for a second. You know, what do you got? You got mg this way, and you got, mg that way indeed, the normal force that way. And the reason she's right that it's also mg that way is because we're not accelerating off the plane, right? We're staying acceleration 0 up and down. So those forces have to balance. And indeed, the normal force is mg. So the normal force is mg in this case. Now, on the other hand, the car is doing what? It's going in the circle, right? So if I draw in this picture, there is, you know, the friction force is actually in that direction for this motion. Interesting.
But wouldn't it still be force of friction equals mass?
Yeah, so the force of friction, this is a circular motion problem. So we see force of friction is equal to mv squared over r. All right? But the force of friction is what? It's mu times the normal force. And so that's mu mg. And you find out that this problem, the book was very kind here by telling you the mass. It didn't have to, right? This problem makes sense if they don't even tell us that the mass of the car is 1,200 kilograms. All right? In other words, the masses cancel, right? And we just get v is equal to the square root of mu gr, I think. So that's the square root of 0.65 times 9.8 meters per second squared times, I think it was 90 meters, whatever that works out to. Does that make sense? Listen, I don't think 7 is like way harder than 9 or something. It's just, there's a, well, if you'll forgive the pun, there's a circle of ideas there that I don't really want to test you on because there's a subset of you who get really confused about that discussion, and I just don't think it's fair for Tuesday's test. This, on the other hand, I think is pretty much almost the same as that problem. Yeah. All right, that was number 9. Next on my list that I've stolen, I'll give it back to you in a moment over there. Number 11. How many revolutions per minute would a 25 need to? How many revolutions per minute would a 25 meter diameter Ferris wheel need to make for the passengers to feel weightless at the topmost point? I am again not going to test on this because it's also the same as problem 7. We'll test on that later, okay? I'm moving these questions. If you've already worked on it, that's good. It will come back later in the course, okay? So right now I'm going through page 132 and confirming or denying the importance of problems, yeah? Where are we? 13. Space station, circular tube. How many rotations? I'm going to, again, remove that one. 13 is out.
13.
Page 132. Number 19. Again, I will not ask you about number 19. 25. Here we have a car. Not for the test. 25, don't worry about it just yet. Let's see here. 27. Particle involves in a horizontal circle radius 1.95 meters. At a particular instance, acceleration is... Okay, 27, part A, is possibly tested because we spent about 20 minutes going through that last class. All right? So that 27, part A. I said part B, not just yet. 28. Calculate the force of Earth's gravity on a spacecraft 2 Earth radii above the Earth's surface if it has a mass. That is completely fine. Gravity questions are allowed. We have spent time on gravity. 28 is okay. 28 is okay. 32 is okay. Oh. I like that problem, though. So put it on the test. Nothing to hear there. So I meant 29. 29 is okay. The ones on gravity are probably going to be okay. If I can stay on the right thing. 29, 31. 31's fine. 33 I think is fine. These are all going to be gravity. Yeah, 33 is fine. 35 is fine. 37's fine. 43 is good. And let's see here, 40. A space shuttle releases a satellite into a circular orbit 780 kilometers above the Earth. How fast must the shuttle be moving relative to Earth's center when the release occurs? Yeah, I think that's actually a reasonable question. 45. 49. Yeah. I'm trying to avoid problems that involve the things I've already ruled out with the circular motion. And I think we've done that. Let's see here. Let me check the last one. 73, 75, 89. What are those? Oh, yeah, 73 is out. 73 is out. It's another one of those. 75 is actually fine. What was the other one? 89. Yeah, 89 is fine. So basically what I've done is just to rule out questions that involve the study of free body diagrams in circular motion. Well, that's not quite honest. I did say number 9 was okay, but anyway, yes?
Have you decided how many questions you want?
How many questions should we have on the exam? 10? I don't know. I usually tell students enough, right? I mean, what? It's not funny? I think it's funny. I mean, there should be enough questions to test the material. How many? I don't know. I mean, I'm not giving you multiple choice for the most part. I mean, it might have a few, like short answer, fill in the blank, like a blah, 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 fill in the blank, blah, 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 fill in the blank, you know? Like, that's the kind of question, that's the closest thing I get to multiple choice in here. I will not probably ask multiple choice because I don't like them. They're a pain to write. I prefer to ask short, here's a problem, find one or two or three things, and you work it out, and I can give you partial credit if you're half right, or full credit if you're all right. This is physics, so make sure your answers have appropriate units, right? Units are important for answers. I do not take off points if you don't have units in the intermediate steps. So if you want to work with just numbers without units in the intermediate step, go nuts. That's fine. Just remember that the answer must have appropriate units. Now, that would be an anathema to many physics instructors, but that's just the kind of easygoing guy I am. So, just kidding. No? It's a tough crowd. Yes?
We can take points off if we find the correct answer but don't show all our work, don't show how we got to a certain point.
Well, I take points off if you have the correct answer but no work. Well, there are varying degrees of this. The question is whether or not I think it's preposterous. Or it's also possible that I could take points off if you show work, but the work is the wrong work and you got lucky. Like, there exist ways that you can get the right answer to problems, and yet your work is total nonsense. So yeah, I would try to take off points for that. I'd like to think my grading was careful enough that I would take off points for that. There exists the chance that I might not notice. But I hope I would notice and take off your points. So, yeah. You are allowed a sheet of notes, right? Front and back. You can put examples on there if you want. You can. I will provide things like mass of the sun, mass of the earth. I will not tell you what G is, but if you ask me, I would. I mean, like, I'm not going to put G on the test, is my point. If you ask me, like, I forgot what G is, I would be sad, but I would tell you. Yeah? You have a question? Oh, yeah. Yeah. That's a lot of the reason I prefer short answer for physics as opposed to multiple choice is that it gives me a reasonable method that I can give partial credit. I can, and the way you guys get things wrong, it's so nuanced and many, I mean, there's so many different wrong ways. I don't, so I don't even, if you're looking for me to publish a rubric, I wouldn't do that because I can't even describe all of the possible wrong ways to do a physics problem. Like I just grade on the basis of general wrongness. Is it like half wrong? Is it 2/3 wrong? But this is all irrelevant because you guys are going to get every problem exactly right. And so I will just be like, oh man, this is so boring. All the right answers and all the right work again and again and again. This is such a boring thing to grade. That's what I'm looking forward to. All right? Okay, that's good. Yeah.
In terms of rounding,
Oh, rounding. Yeah.
partial credit or...
Oh, you're still talking about grades. Oh, significant figures. I'm not testing on significant figures, so.
Like if the answer is like 150, you get like 146 or something.
I do, as a general rule, want you to give me four digits to the answer, without attention to significant digits. Yeah. So it's conceivable that the significance figure answer could be 150, whereas the answer I'd actually like to see you give me is 149.6. Now, will I take off if you give 150 instead of 149.6? That depends on the reason for you giving me 150. If the reason is that you used an incorrect equation, then yeah, I'm going to take off points. If the reason is that you just rounded something mid-calculation, I'm probably not going to take off points. But you got to be careful. Every once in a while, there's some problem that making a round-off error in the middle makes the whole analysis get like way more complicated, and it's dangerous to round. Oh yeah, no, I'm not using part of the Tuesday meeting for lecture. No, it is all exam. Will it take the whole time? Oh yes, it will. Yes, sir. The questions will be evenly distributed in some sense. I mean, yes, they will be distributed amongst the material that's been covered. So that would include the chapters, but also three-dimensional vectors, which we have talked about in here, right? So, just to get to the point, here's a potential test question. But if I had to guess, to actually answer your question and not just ignore it, more or less, I would foresee the test being about 40% kinematics, about 40% dynamic, well, maybe about 30% dynamics, about 30% gravity. So 30% like free body diagrams, that stuff, about 30% gravity / circular stuff, about 40%. The kinematics, remember the projectile motion and all that good stuff. What am I to?
Kinematics, dynamics.
Oh, that's 100, isn't it?
Yes.
So then another 5% on vectors, something like that. So here's a good question. I don't know. We could have vector A is 271 in meters. Vector B could be 0, 1, and 3 in meters. And I could say find the angle between these vectors. Like that. That's a decent question. If you've been paying attention here, you ought to nail that. Or I could ask something more fun, like find the angle. Have you guys ever been asked this question? I don't think I've asked it or answered it in here. It's kind of a fun question. Think about a cube, right? And so let's suppose it's a unit cube, right? So like a foot by a foot by a foot by a foot by a foot. What would the coordinates be of this? 1, 1, 1 foot. So what I'm doing is I'm putting the origin back here. Yeah? And then I can ask the question, what's the angle between the vector which connects the origin to the 1, 1, 1 point and the vertical leg that's also coming out of the origin? Yeah? So what do you guys think that angle would be? What's the angle between like this guy and this guy? Any guesses? 45. Thank you. I wanted you to say that. So let's see here. 45 degrees is the alleged angle. But you see, we could figure that out with vectors more concretely, right? What's a vector? What's this point up here? It's 0, 1 foot. Oh, I'm sorry. It's 0, 0, 1 foot. Yeah. 1 foot. So it goes 1 unit upward. It's the vector 0, 0, 1 foot. Yeah. And the b vector is the vector 1, 1. I don't know. You can draw the foot afterwards or in each component. You pick it. Anyway, this is a and b. Those are the vectors. What is the angle between them? So what's a dot b? A dot b is what here? 0 plus 0 plus 1 foot squared. So it's 1 foot squared, yeah? One square foot is the dot product in this case. What's the magnitude of A? What's the length of A? It's 1? Well, 1 foot, right? The magnitude has the same units as each component. What's the magnitude of B? No. It's the square root of 1 plus 1 plus 1. So it's actually square root of 3 feet. That would be the length of that vector. Now you guys saying 1 is consistent with your guess of 45 degrees, but it's unfortunately not true. So we had a theorem which says that this is AB cosine of the angle. Yeah? So in this time we get cosine of theta is equal to, 1 over the square root of 3. The feet squareds cancel. So theta is inverse cosine of 1 over square root of 3, which is what? About 57.4 degrees. Give or take. So pictures can be deceiving, right? And what's wrong? So what was wrong with what you guys thought? Why did you guys think 45 degrees? Is because you, what's that? It's half a 90. Right. But the thing is, if you were to look at that, if you were to look at the plane, the vertical plane, which contains the point that we're pointing to, the 111 point and the 001 point. So this is a different picture of that. Right? So in this picture, you can see more clearly what the problem is. This and that are the two things we're looking at. We're trying to find this angle theta. The thing is, it's not a square. If you cut it like that, it's actually a rectangle, which is why it's not 45 degrees there. And it's in fact about 57.46, I forget. But I always give this as an example to try to convince students that vectors are worthwhile tools to divorce yourself of geometric mistakes in 3 dimensions. Because pictures, 3-dimensional pictures on a 2-dimensional page, they don't really do justice to things, right? But if we choose a system of coordinates, then we can answer concrete questions about 3-dimensional objects using vectors. For example, you guys have taken organic chemistry, yeah? Some of you? So you guys do that thing with the tetrahedron, right? Something like this, yeah? And you find the angle between the legs in this thing, don't you? Does this sound familiar? There's like 100 and some odd degrees. You guys know what I'm talking about. Well, if you were to embrace vectors, you could actually find those angles by doing 3-dimensional coordinate geometry using vectors. That is not a nice test question. I haven't formulated it clearly. This is a question I sometimes ask on the final in Calculus 3. And a lot of times there's only maybe 10% of the students who can get it, because it's easy to ask geometric questions which are really difficult, actually. Now, this is a good question for your test because I've done it a few times now. How would you do it now? Same thing that we just did, right? We calculate A dot B. Then we calculate the magnitude of A, we calculate the magnitude of B, and we use the purple formula to find the angle. Should I go through it?
Please.
All right. So what's A dot B? So we've got 0 times 2, 1 times 7, 3 times 1, meters squared. So in this case, A dot B is 0 plus 7. It looks like 10 square meters. What's the length of A? Length of A is the square root of 1 plus 9 meters. In other words, square root of 10 meters. What's the length of B? The length of B is the square root of 4 plus 49 plus 1. That's the square root of the sums of the squares. Square root of 54 meters. So cosine theta is, again, A dot B divided by the product of A and B, which in this case is 10 meters squared divided by the square root of 10 times the square root of 54. 54 meters squared. So the meters squareds cancel, right? And we get theta is the inverse cosine of 10 over the square root of, properties of square root? What is the square root of 10 times the square root of 40? Square root of 54. Can you just write that as one square root? You can, because the square root of A times the square root of B is the square root of AB. So in terms of calculator work, this is much easier if you just go square root of 540. You could simplify it further, but that's not really the point here. So let's get to it. Make sure I'm in my degree modes. You're like, if I give the answer on the test in radians instead of degrees, I'd be like, well, I probably would take off points either because you didn't write down degrees or you didn't write down radians. Now, if you write the right answer down in radians when I've asked for it in degrees, I probably wouldn't take off points, but I'd just be annoyed. Right? That makes sense? So if the answer is like 1 radian, but I say, give the angle in degrees, and you're like 57 point whatever. Whoa, is that a radian? I don't know. I got distracted here, guys. I got 64.51 degrees there, okay?
Wait, oh, I see.
So there you go, that's the angle between the vectors. So I said you should put units on answers, so I guess it's debatable. Some people say that degrees are degrees units, or are they a system of measurement? I don't care. Anyway, if I ask for an angle, I would like it to probably have degrees, all right? If you happen to be in radian mode, and you write the answer in radian mode, I will still give you significant partial credit. I probably will give you full partial credit if you write radians, but then I'd be like, why are you doing this to me? I asked for degrees, you know? It's not nice. I might look for other ways to take points off your test. I'm human. I can be petty.
Hey, John,
Yes?
I have a
What?
question. I think you switched A and B.
Oh, no!
Wrong? Yeah, because I
Ah.
was up anchor back.
Ah.
Yeah, Josh was like, just change the letters. There you go, John.
Meh.
It's still should be. It's okay.
See, the nice thing about angle measure between vectors is that the angle between A and B is the angle between B and A. So like, there's a certain, if I just randomly mixed up the identities of two things in a kinematics problem, it'd probably make me wrong. But here, I didn't get in trouble. I allegedly have, it was alleged I had dyslexia when I was in first grade. My mom, the teacher, called her up. She's like, your son has dyslexia. I'm going to put him in the special class. And my mom was like, well, but you just told me he has third grade math skills. And he can do math that you haven't taught him yet. He's in first grade. I learned in medical school that people with dyslexia have poor math skills. So maybe my son doesn't have dyslexia. Maybe you just don't want to teach him. Or something like that. And then she started homeschooling me. So there you go. Which was really something, because I was in New York State, upstate New York in the mid-'80s. You know, homeschooling was not prevalent then. But she did. And I'm thankful that she did. Of course, now I'm, crippled by my social awkwardness and ability to talk to people because I was homeschooled, which makes me weird. I mean, I'm weird for other reasons, though. Yeah, okay.
I think you're hysterical.
I think being weird is a virtue, though, right? That's our current society's, yeah, something like that. All right. Ask me other questions. Ask me questions about forces, please. I mean, I could do a gravity question if you got one, but whatever.
No, it's too close.
Are all those force questions good that you gave?
I think so. We can pick one, though. Let's pick one. Which one would you guys like to work?
37,
Which one?
page 103.
103, which one?
37.
That's a good one. Okay. Number 37 on page 103. All right. So we are told that a force of 35 newtons is required to start moving a box. And what kind of box are we looking at here? 6 kilograms, right? Across a horizontal concrete floor. A, what's the coefficient? What is the coefficient of static friction between the box and the floor? What's the coefficient of static friction? 7 with me. B, if the 35 Newton force continues, the box accelerates at 0.6 meters per second. find the coefficient of static friction if A equals to, we're given that A equals 0.6 meters per second squared after it starts moving. Okay, so to recap, and to just emphasize the words I haven't written down, what the problem is telling us is that when we get to 35 newtons, the box just starts to move, right? So that means that 35 newtons is at the threshold of the words static friction. So what that means is that 35 newtons is equal to mu sub s, the static coefficient, times the normal force, right? Now, what is the normal force here? Be careful. I would encourage you, don't just assume the normal force is weight. I will test on this. I guarantee you, one of the questions on the test will see whether or not you're thinking that the normal force is always just mg. If we look at the solution to quiz 2, was the normal force just mg? No, it's on an incline, so that's more obvious. But either of the problems, right? In the first problem, the pushing force made the apparent weight, like the normal force was larger than mg, right? And in the second one, anyway, my point is simply this, is that we've got the normal force. All of that said, in this problem, the normal force is just what? mg. All right, so mu sub s is just equal to 35 newtons, glad I'm not walking to my car right now, divided by m times g, which is what? 35 newtons divided by 6.0 kilograms times 9.8 meters per second squared. What do we got? Where is everybody? I guess everybody who's missing today, they already know the material, right? They don't need to be here thinking about physics. Oh, maybe they're all up in Washington, D.C., right? Like that brute squad for, a counter brute squad. Yes, it's here. 35 divided by... I think that'd be fun to go to that thing. All those students up there counter protesting or whatever. If I was single and I had time on my hands, I'd be up there. Yeah, that sounds like a hoot. It's here. 0.5952. You know what I'm talking about? We got like 300 students who are going up to counter protest the protesters up in Washington, D.C. as it respects to the, what's his name there? The new John Roberts. What is his name? I don't know. Kavanaugh? Is it? Yeah. Let's see here. So take a breath. Is everybody good on why that should be the coefficient of static friction? Because that's the amount of force you need to just start it moving. Now, if I applied less than 35 newtons from 0 all the way up to 35, what would happen? Nothing. Like the box would just sit there. It wouldn't be moving. Now, once it starts moving, then we're in the kinetic region. So for part B, the picture is like this, yeah? We've got, still 35 newtons, because the problem told us that. We also got a force of friction the opposite way. And we still have the normal force and mg. This is the free body diagram for part B. The free body diagram for part B I just drew. And so, again, because, there's just the normal force and gravity, we have Fn equals to mg. And on the other hand, we have mass times acceleration is 35 newtons minus the force of, minus mu sub k times the normal force. What are we given? Well, we know the mass. We know the acceleration is 6.6 meters per second squared, right? And what else? Oh, we know the normal force, yeah. So this is MA is 35 newtons minus mu sub k times mg. What am I trying to find? Oh, I'm trying to find mu sub k. This is how I do physics, by the way, guys. You guys, you're crippled by this. Oh, I'm sorry, we don't use that word anymore. You're stuck in a rut by trying to find what we're after, right? Like you can't see past the fact, I need to find mu k, right? But what you got to do is you got to take a step back, you got to relax, and you got to write down the physical laws that apply. After you do that, it's usually algebra that will get you to what you want. But this is what you have to do to be successful at physics, is you can't just chase after what you're looking for immediately. All right? I mean, that's just the name of the game. All right, so mu k mg equals to, what, 35 newtons minus ma. So mu k is 35 newtons minus ma divided by mg. And we can figure out what that is, because we've got all those numbers. So 35 newtons minus 6, what is it, is it 6 or 6? 6.0. 6 times 0.6, and that'll be in newtons, because I did a kilogram times meter per second squared, and I'm dividing by 6.0 times 9.8, and that'll be in newtons as well. We should get newtons over newtons, because mu is a coefficient. It's a dimensionless constant, right? It's a multiplier that has no units. All right, what do we got? 35, what? Oh, sorry. 35 minus, no, I can't see. It's okay, 6 times 0.6 divided by 6 divided by 9.8. I get 0.534. Yeah? Now, does my solution make sense to you guys? I mean, do you have any questions? Sort of? Go for it.
I'm still stuck on the first part.
Oh.
As to how you got 0.59652. If is M the mass of the box?
Yeah.
Where do you use A then?
I don't use A for part A. So the acceleration is only needed for part B. For part A, we're just trying to find the coefficient of static friction. I actually really like this problem. It's kind of nice problem. Yes, sir. 23 on what? Is that the high wire person?
Yes.
The high wire one? Okay. Oh, this is good. We haven't done anything quite like this. It's a good problem. Let's see here. That red marker, it does not come off easy. All right, so we've got Arlene is to walk across a high wire strung horizontally between two buildings 10 meters apart. The sag in the rope when she's at the midpoint is 10 degrees, as shown in the figure. If her mass is 50 kilograms, what's the tension in the rope at this point?
What number is this?
Number 23. Page 102, yeah. And so Arlene is in the middle. Arlene will look like Mr. Top Hat, though, for illustrational purposes. And this is given to be 10 degrees, which, of course, is not accurate to my picture. The question then is, what's the tension in the rope? All right? So this is an equilibrium problem, right? She's not accelerating. I mean, if she's accelerating, it's not good. Unless she's just like in the forward direction. But we're not told anything about that. It's not a forward acceleration problem. This is a problem of balance. So the free body diagram will help us out. What are the forces at work here? Right, so basically we got gravity, mg, and then, well, the normal force, right? And those must be balancing, I suppose. Where's the normal force coming from, though? It's coming from the tension in the rope, right? So if we draw the tension force here, I would have to draw it really, really big in order to appreciate what's going on. We do that, just to be ridiculous. So the tension force at the same scale as I've drawn mg and Fn would have to be something like this. Well, maybe it would. Maybe something like this, because it's also pulling this way, yeah? I mean, at that one point, the rope pulls up. It pulls both ways. I mean, like that, right? At this point, there's this tension, there's that tension. I mean, if you look at the tension, there's two pieces, right? There's this piece, and there's that piece to the tension force. There's the T cosine 10, and then there's the T sine 10. And likewise over here, there's T cosine 10 that way, and there's T sine 10 this way. So what's happening with the tension of the rope on the point where the person's balancing is that the horizontal parts of the tension force are canceling out, right? Because otherwise, that point in the rope would be accelerating one or the other, which would be weird. So the horizontal parts of the tension must cancel out. And the vertical parts of the tension, well, that's where the normal force is coming from, right? So what I'm trying to say is that 2t cosine of 10 degrees is equal to the normal force. But that's also equal to mg. I do mean sine, thank you. Thank you, thank you. What don't we know here? What are we given? I forgot what we were given. What were we given? Oh, they gave her mass? Oh, that's helpful. Was it 50? I'm remembering 50 kilograms. So, oh, hey, we can solve for t. T is equal to 50 kilograms times 9.8 meters per second squared divided by 2 times the sine of 10 degrees. What does that give us? Now, sine of 10 degrees is pretty small. So I get 1,410 point, like, I don't know, if I write 5 numbers just for the sake of being different. 1410.9 newtons. So, or you could say 1,411 newtons if we stick with my usual rule. Yeah. Yep.
Why is the normal force set equal to mass times gravity?
Because if we, so the blue is the forces on Arlene. So on Arlene, there's just the normal force from the rope pushing up and gravity pushing down. And Arlene's in equilibrium, right? She's not accelerating up or down. So that means that the normal force minus mg has to be equal to 0, so they have to be equal.
So would it be mg plus whatever the tension force is?
But the tension force is where the normal force comes from. That's where the normal force is coming from. It's the tension in the rope pushing up. It's not a separate force. I mean, it's the source of the normal force. So, this was an odd problem, yeah? Is this the answer? Okay, good. All right. So, at least I agree with the book. So either I'm wrong and the book is wrong. I mean, it's possible. I don't know. I think this is how to think about it, though. Let me stop kidding. Other questions? Yep.
Can we look at number 35 from that same chapter?
It's the pulley problem. Suppose the pulley is suspended by a cord C. Determine the tension in this cord after the masses are after the masses are released and before one hits the ground. Ignore the mass of the pulley and the cords. So I'm pretty sure the answer should just be the weight. I think it's just the weight of the masses. So it should just be like 3.2 plus 1.2 times g. Is that not the answer?
They got 34 newtons, so that's
Well, let's see here. That times... Oop. I get 43.12 newtons.
yeah. So how did I was just confused how to do that.
Sure. I'm sure I can find a more confusing way to explain it. Let me work on that now. So this is M1, and this is M2, yeah? And this is... What number was this? 35? Page 103, give or take, yeah? So the point is that the question is, what's the tension up here, right? So just to recap, I said that the answer should be... What?
The answer was 34.
Oh, what?
Yeah, that's what the book said.
What have I done wrong? Oh, no.
This is chapter 4,
35. Well, I wonder what maybe I'm suffering from some blind spot in my... Now, admittedly, my logic was not... what was my logic for saying that it's the sum of the masses times gravity? I didn't give you any logic. I just said that should be the answer. So that is a little bit suspicious on my part, that I've not given an explanation. Yeah, it says 34 newtons. All right, let's try to think through it. Where is that tension coming from? Why is there a tension in the supporting cable C? Yeah, I think it's because there's this tension here. Let me call them T1. Let me call this one T2 for the sake of just discussion. Yeah. So those two tensions are pulling on the pulley, right? And what's pulling up on the pulley? The tension we're after, right? The tension in the cable C. So I think it should be somewhat clear that this tension should be equal to T1 plus T2, right? Does that make sense? I mean, because but then, but we also know that the string's not stretching, right? So let's suppose that the motion's this way, just for the sake of discussion, all right? And so we know that M1A is equal to what? It's equal to M1G minus T1. And we also know that M2A is equal to what? It's equal to minus M2G plus T2, actually. So if I want to find what's T1 plus T2, how do I get that here? How about if I take, let me call this equation 1, let me call this equation 2. How about if we look at equation 2 minus equation 1, what's that give me? We've got m2a minus m1a equals to, I'm going to go to the other board over here if it's okay with you guys, equals to minus m2g plus t2 minus m1g plus t1. Or I can put a minus and a minus to emphasize what's going on here. Yeah. Anyway, my point is after you subtract the equations, what I think you'll get to is that m2a minus m1a equal to, what is it? I can't do math. What's wrong with me? Minus m1 plus m2 g, and then t1 plus t2, t1 plus t2, yeah? Let me clean it up a bit. What I've just figured out is that t1 plus t2 equals to, well, I'm trying to see a simplification. I don't see it yet. m1 plus m2 times g plus m2 minus m1 times a. What did we figure out the acceleration was in this problem before? Do you guys remember? We worked that out. We figured out what the acceleration was for this problem. Oh no. Do I even know M1 and M2 here? I think these are... I do? Oh. And you guys have figured out the acceleration? I mean, we had a general... You'll forgive me. I'm thinking of solving this problem for arbitrary M1 and M2. I think we could actually do that if you think about what we already did in here. I believe I showed the formula in a previous lecture that the, how's it go? I think it's the difference of the masses divided by the sum of the masses was the formula we derived. So what was the, I believe the acceleration formula I found before was something like m1 minus m2 over m1 plus m2 time, what's that? And so we have previously derived that, and I can put that together with what we just did. So in other words, I'm going to take this and put it here and see what happens for us. T1 plus T2, M1 plus M2G, plus M2 minus M1 times M1 minus M2, G divided by M1 plus M2. Wait. Which is what? M1 plus M2 squared plus what? Plus M, well, sorry, I'm having trouble multiplying this out. So the cross terms cancel, and I'm just left with minus M1 squared minus M2 squared? It seems wrong to me. It is what it is. And I'm not done yet. I divided by, so guys, what